Chat. Today we are going to talk about how OpenRelay makes use of Docker. So, as a high-level introduction, OpenRelay was designed to run in containers. It doesn't strictly have to run inside Docker containers, although that is the most convenient form of containers we found to use. But broadly speaking, it was meant to run in an isolated, orchestrated sort of environment. Docker drastically simplifies several aspects of running OpenRelay. It simplifies the development process because it's easy to get all of the processes that we need up and running on one developer laptop at a time. It simplifies our build processes, and we'll talk about how we use multi-stage builds a little later on to make sure that when we are doing a build, the only thing we need to have on that machine is Docker. It simplifies our deployment process because we can just push to a Docker image registry and pull from there and not have to worry about many of the intricacies of where are we going to put our packages, how are we going to tell which machine which packages it should have, how are we going to do subsequent configurations, things like that. It simplifies our service management capabilities, so we don't have to worry about things like systemd service files. Docker will automatically restart a service if it crashes. It will manage moving Docker containers from one host to another if there's a problem with the host. And then finally, Docker also simplifies our auto-scaling capabilities. So if we run out of capacity as we're processing a bunch of orders, we can add virtual machines to our cluster. We can add containers that are processing a particular queue, and everything scales up and down very easily. There are other things that Docker helps with, but this was the most immediate, obvious list of ways that Docker has simplified our lives. So for those of you who don't know what Docker is, we'll start out with that. Docker starts out with an image, and an image is a snapshot of all of the files necessary to run a service. You can kind of think of a Docker image as being like a virtual machine image, and generally speaking, a Docker image will include the bulk of an operating system. It will include possibly a package manager. It will include things like C shared libraries, Python shared libraries. It'll give you a bash shell, things like that, all the different things that you would conventionally have on an operating system. In order for a Docker service to run, that image must include all of the user space dependencies. Now, the kernel comes from the host machine, but anything that would traditionally be in the user space, so again, that's things like shared libraries, shells, other dependencies, those have to be found in the Docker container. And so generally speaking, Docker containers take the form of small Linux distributions. Finally, images are defined by a Docker file. So that's just a single file that you can keep with your code that describes exactly how this service is meant to be built. One of the really neat things about Docker is that Docker file doesn't really care what's underneath it. You can package a Java application, a Node application, a Go application. You can use Maven for dependency resolution, NPM for dependency resolution. You can use pip for dependency resolution. All that doesn't matter. All of those things are viable options. And so long as your Docker file tells what commands to run, you can grab whatever you need, shove it into this Docker image, and have a single deployable package that doesn't care about the underlying system that was used to develop the code. Next, we have the image registry. So after you have an image, you can take that image and you can upload it to a shared registry. So there's a public registry at hub.docker.com, but it's really easy to host your own private registry. And whether you're using Docker Hub or your own private registry, you can easily pull images from a registry. So this makes it easy for developers to share dependencies with each other. It makes it easy for deployments to just pull an image from an image registry and deploy it at runtime. And nicely, that also means that what the developers are using on their local machines, if they're running on the same images that are running on production, you have a high level of confidence that you're going to get the same results, where the classic developer works on my machine. At least several variables are removed if you're doing your development with Docker and using a shared image registry to make sure that what is running on production is exactly the same thing that was running on the developer's machine. So the next concept in Docker is a container. So container is a live version of an image that's running on the host kernel. So I mentioned earlier that a Docker image is kind of like a virtual machine image. So the container is kind of like the virtual machine, but it's sharing a kernel with the host. So the Linux kernel contains some isolation capabilities that make sure that containers are not able to interact with each other outside of certain permitted ways. So one Docker container is isolated from other Docker containers and isolated from the host system in a way similar to how virtual machines are isolated from each other. However, with virtual machines, each virtual machine gets its own instance of the kernel, which of course carries a lot of overhead. So by sharing the host kernel, you're able to cut away a lot of overhead, but there's also a slight reduction in the level of isolation between containers than you would have with virtual machines. So as I noted, containers do not touch the host user space unless they are specifically granted permission to do so. And generally speaking, Docker containers only run one process per container. So where virtual machines, you would often expect, okay, we're going to be running an SSH daemon, we're going to be running Apache, maybe a firewall and a bunch of other things. Generally, your Docker container is only running the one process that is the purpose for that container's existence. So a next property of containers is that generally they are started fresh from an image every time they're executed. So if you had a Docker container that you thought might have been compromised or there was something weird going on, if you just kill it and start it from a fresh image, you're back where you started. This gets into a concept called immutable servers, where you don't rely on anything on the server that wasn't put there by a deployment process. You don't expect the Docker container, in this case, to keep track of anything over a long period of time. You would put that into a separate database or some separate shared content store, not within the Docker container itself. So finally, after you have your images and your image registry and your containers, you have your stack. And stack is a little bit more of a loosely defined concept within Docker. Like there's a very clear concept of an image, a very clear concept of a registry and a container. There's a few different ideas of what a stack looks like, but essentially a stack is a collection of containers that are networked together. They may run on the same host or they may run on a networked cluster. The containers within a stack will communicate with each other over network-based protocols. So it doesn't really matter if they're on the same host or not. They're going to be communicating over a network protocol, even if they're on the same host. So if they're moved to different hosts, they're still communicating over the same network protocols they would have been using anyway. So there's different forms, as I mentioned, there's different forms that stacks can take. A little bit later, we're going to be looking at a Docker Compose file and how that stands up a collection of different containers that need to communicate with each other. Docker Compose translates kind of cleanly onto something called Docker Swarm, which is a way to network clusters together. OpenRelay uses Amazon Web Services Elastic Container Service to manage our Docker stack. Another popular mechanism for managing stacks of Docker containers, and I don't think they really use the term stack, but Kubernetes does a lot, is a very popular way to manage a bunch of different Docker containers. So does anybody have any questions about Docker before I move on? Images, registries, containers, or stacks?
Seems easy enough so far.
No questions?
No, I'm good.
Okay. So now we're going to talk about OpenRelay's images. So OpenRelay is written in Go, and Go has some really neat properties when it comes to Docker. So while a typical Docker file would look something like this, and this is just an example I pulled off of the internet, you can probably Google that guy's name and find this package. But this is basically just an Apache 2 package. So here it says from Ubuntu 12.04. So that is the base image that this Docker image is being built from. So essentially, it will pull the Ubuntu 12.04 image from Docker Hub and then apply the rest of this stuff on top of that. So it tells us who the maintainer of this image is. Then it runs this big long command to install a bunch of packages and then remove some stuff. And all of the stuff that gets installed at that point will be captured as a part of this Docker image. Then it sets some environment variables. Those can be overridden at runtime if you need to, but this sets the default values. Then it exposes port 80 that basically tells Docker that other services may want to communicate with this Docker container or Docker containers derived from this image on port 80. And finally, it says that the command we're going to run when somebody says, run this Docker container is this. So this is a list of the command and the arguments that are going to be executed. So this is a fairly typical Docker file, but this is not what OpenRelay's Docker files look like. So OpenRelay's Docker files look more like this. So they say from scratch, and in this case, scratch is an empty image. So that Ubuntu image we were looking at a minute ago was probably derived from the scratch image, or one of its parents was derived from the scratch image. A scratch image has no files in it whatsoever. So this Docker file, in the OpenRelay Docker file, we're going to copy from the bin/delay relay file into /delay relay on our Docker file, or in our Docker image. And when we run this container, we are going to run /delay relay. Because Go is a statically linked language, everything that we need to operate, so long as we have a Linux kernel, can be found in the delay relay binary. So in the example that we have here in this Docker file, the presumption is that we have copied, or we have built bin/delay relay on our host system, and then we are copying it in from the host system into our container. So this, instead of having an entire operating system, or at least the bulk of an operating system within our Docker image, we only have this one file. And that has a lot of advantages. The most obvious advantage is that it's very fast to pull. When we are doing a deployment, or if a developer is pulling something, if the only thing in the container is this one executable, it will pull a lot faster than it would pull if you were grabbing all of the files in an operating system. Another neat point about it is that it drastically reduces your attack surface of your container. So if we have a networked Docker container and somebody manages to get that Docker container to do something it shouldn't, they're very limited in what they're going to be able to get it to do. They can't, execute other commands. The only command that they have to execute is whatever command that Docker container was built to run. They're not going to be able to get a shell and do other nasty things because there is nothing else on that Docker container that they could get access to. So that Docker container or Docker file that I just showed you is a little bit of a white lie. We don't actually build on the host system and then copy it in. What we actually do is something called multi-stage builds. And we're actually kind of reworking the way that we do multi-stage builds at the moment, but this is how things have been built so far. With a multi-stage build, we say from Golang 1.8 as core build. So we're giving our first image a name. We're going to make this directory. We're going to basically change into that directory, but we have to use the Docker terminology for changing into that directory. Then we copy the directory that has this Docker file in it into that directory. So we're copying everything that in the folder adjacent to this Docker file into the Docker image. Then we run make clean bin. So there's a make file. It has instructions for cleaning everything up. It then builds the binary folder. That's going to take a while. It's got a lot of stuff it needs to build. And obviously, this Golang image has all of the binaries that you need to build Go binaries. It's capable of dealing with a make file. So there's lots of other dependencies on this core build image that we've just created. But we don't want those to find their way into the final image that we're generating. So then we can start with a second image. So as soon as we have this from statement again, we're starting on a second image. And this is going to be the image that actually gets tagged at the end of this build. So again, we're starting from scratch. So this is going to be an empty container. Then we copy from core build the file in this folder that we built a minute ago, and we copy that to delay relay. Then again, we just run delay relay when somebody executes this container. So the advantage of this approach is now anybody who has Docker on their machine can simply build this Docker file. It will go out, grab the Go dependencies that they need through the Golang 1.8 image that they can pull down from Docker Hub. That has everything that they need to do the rest of the build. Then from there, they just copy those files into an empty image, and they're off and running and able to get a build up and running. They don't have to worry about having a Go development environment on their own system. Or if they're building on Linux or Windows or Mac, they don't have to worry about building Linux-based binaries that are going to play nicely within the Docker container. So this has really streamlined things and made it easier for some people that we've been working with on GitHub to get up and running, building OpenRelay, and running things on their own. Does anybody have any questions about OpenRelay's images or the typical image I talked about, the Go images or multi-stage builds?
I don't have any questions.
No questions.
Okay. So now we're going to talk about OpenRelay's development stack. And we're going to run OpenRelay's development stack. If you guys are following along, there's a series of commands on the next couple of slides that you will be able to run if you want to try and get OpenRelay running up on your own machine. So to set up the development environment, first you need to clone the OpenRelay Git repository. So that's going to be git clone https://github.com/notegio/openrelay.git. Give that a moment to check out, and then cd into that directory that it just created. Then you need to check out the V2 support branch. I've put some optimizations in the build process into the V2 support branch that aren't present in the master branch. they'll be merged into the master branch soon enough, but they're not there yet. So if you want to run, if you want to follow along, you'll need the 0xv2 support branch. Once you have that checked out, you can run docker compose-f docker compose-testrpc.yaml build, and that will build all of the Docker containers on your local machine. That's going to take a while, and we're not going to, if anybody is following along, I'm not going to wait until it's done building to move on to the next slide. You guys can follow along, and then I hope by the time we get to the end of the presentation, you should be up and running, and you guys can ask questions if you need help. Once you've executed the build, you would run the same command except with up, and that will start all of the containers. Once those are running, you will have to Control-C to close them out, and then you need to wait for all of the containers to close. Then you can run the same command one last time with an RM, and it will remove all of the Docker containers described in that stack. So the docker compose-testrpc.yaml is a manifest file that describes all of the containers that we're going to need in a stack. We will look at that in just a minute. And because of the way the OpenRelay Git repository is currently set up, you have to specify the manifest file. If I had been smart enough to call that file docker compose.yaml, you wouldn't have to specify it at all. But I have another file with that name that nobody uses, and I should probably get rid of. But for right now, it's there, and you have to specify this other file. So now we're going to take a cursory look at the Docker Compose file. The real Docker Compose file is several hundred lines long, and we're not going to bore you with all of that during the presentation. But we are going to look at the general, what a Docker Compose file looks like at a high level. So first of all, we're using Docker Compose version 3. So this tells it how to interpret the rest of this file. There's some things that have changed from version not specified to version 1 to version 2 to version 3. There might even be a version 4 now. I don't know. Version 3 was current when I started this file, and it still works, so I'm still using it. Then we have our services section. Most of what we're going to define is going to be in our services section. Then we start in, we define a service called Redis. Redis, if you're not aware, is an in-memory key value store with a bunch of neat capabilities. OpenRelay uses Redis as its message passing system, so it gets very heavily used. The image that we're using for this is Redis :Alpine. So Alpine Linux is a very small Linux distribution that is commonly used for Docker containers because it's very lightweight. I think the entirety of the Alpine Linux base container is somewhere south of 10 megabytes. So this is basically Redis running in Alpine Linux. And if this is your first time running this Docker Compose file, or any Docker Compose file, or any Docker image, it will go out and it will retrieve Redis from Docker Hub, pull it down so that it can run it in your Docker Compose stack. Then we tell it that we need to expose port 6379. That is the port on which Docker runs. And that is basically telling Docker that some of the other Docker containers are going to want to talk to this container on port 6379. So it will make the appropriate network adjustments to deal with that. This deploy section is mostly pertinent if we are deploying to a Docker swarm. But here we're saying that we want one replica of this image. And for a restart policy, we want to restart Redis if it fails. So if it gets shut down cleanly, then we don't want to restart it. But if it exits with a non-zero exit code, we are going to go, Docker is going to say, oh, that wasn't supposed to happen, and it's just going to restart Redis so that we're back up and running again. Similarly, we do the same thing with Postgres. We need a database, so we're just going to pull the Postgres image from Docker Hub. Now, I would note, in production, we don't use Redis in Docker. We don't use Postgres in Docker. We use separate managed services for those. But for a development environment where you want to get everything up and running quickly and easily, you can put those things in Docker and everything will integrate nicely and everything will be up and running quickly and smoothly through just that one Docker compose up command. You can see that we can set environment variables here. So in the case of Docker, we're saying that in the case of Postgres, we're saying that the password for the Postgres user is going to be secret. Again, not something you'd want to use in production, but it's fine for development environment. And then again, we want one replica and we want to restart if the system fails. Now we get into our own containers that we have defined through Docker files that ship with OpenRelay. So here we're setting up our Ethereum node. So instead of having an image file, like here we said we're going to pull this image, here we're telling it how to build this Docker container. So we're saying that the context, that's the directory that we're going to be in when we build this, is the same directory as the Docker compose file that we're currently looking at. And the Docker file that we're going to use is called dockerfile.testrpc. TestRPC is a system, and we'll talk about this in a little bit more detail in a few minutes, but TestRPC is basically a fake Ethereum node that is very useful for testing your applications without having to worry about getting Ether and spending and waiting for transactions to mine. Everything happens very quickly on TestRPC, which makes testing a lot more pleasant than it would be if you had to wait for things to happen on a real Ethereum node. Then we're also going to set up ports. So this time, instead of saying just we need to use port 8545, we're saying that we want to expose port 8545 as localhost port 18545. So I separated out the port for this stack from just being the regular 8545 in case anybody's running their own Ethereum service that would conventionally be on 8545. So we're separating it out a little bit. But what this will do is it will allow you as a developer to interact with your Ethereum node without having to hunt down what virtual IP address Docker assigned to this particular container. Again, we have our number of replicas and our restart policy. Then we're into our ingest container. So the ingest container is one of the services that is going to comprise OpenRelay. Again, we specify a build context. We tell it where to build a Docker file, what Docker file to build. This time we also specify an image. So we can specify both the build and the image. You can do a pull and you can get it from the image, or if you haven't pulled first, then you can do a build and it will build from it locally. We also specify a tag here. So if you run Docker Compose with the tag environment variable set, then it will look for specific tags of the OpenRelay images that we're building, and it will allow you to push tags if you are a member of the OpenRelay team and able to push to our Docker repositories. But basically, this allows us to change the tag names through an environment variable and use the Docker Compose file for builds and deployments. Then here, for the ingest service, we expose port 8080 of the ingest service as port 8081 of localhost. So once you have Docker or OpenRelay up and running on your system, you will be able to post orders into localhost port 8081, and that will be where the ingest service is running. So the ingest service is just going to run the command ingest. It's going to connect to the Redis host. Again, the Redis host can be changed by an environment variable. There's probably not a whole lot of reason you would do that in the development environment. We specify the relayer address that's going to be suggested when people ask what they need to do to set fees. And then we have the ingest queue that things are going to be sent to after the orders have been received. The last thing I want to note here on the ingest container is that this depends on the Redis container, which means this file or this container will not try to start up until the Redis container has started up. Now, unless we also specified health checks for the Redis container, that doesn't necessarily mean that the Redis container is up and running properly. That just means that it has started. It may not be accepting connections yet, which is part of the reason that we want to have a restart policy on failure, that if this is trying to connect to Redis and fails before Redis has come up, then it's just going to restart. The stack is going to restart the ingest service until Redis has come up, and then we'll be off and running. The last, we also have the exchange splitter service. This goes on and on and on and on and on. I'm not going to bore you with all of these, but basically each service follows the same pattern. We have how we build the image's name, the command that we're going to run, what it depends on, and how to restart it if it fails, or whether we should restart it if it fails. Some notes about the development environment. It uses Ganache, which used to be called TestRPC, which is why we call the Docker image TestRPC, to simulate an Ethereum network. So the Ganache service that ships with OpenRelay uses a standard set of test accounts. So don't think, oh, hey, I have these private keys. I can use them on mainnet, because everybody else has those private keys too. And we see people doing that. Like if you look on Etherscan, you will see people trying to use those public keys that ship with Ganache, and people lose a lot of Ether by making that mistake. But part of the reason we ship with those standard set of test accounts is that we have pre-deployed the contract, and we have pre-distributed the Ether and the token balances. So there are several tokens available within the OpenRelay Ganache Docker container, and those are already assigned to the account. So you've got to use the same keys in order to have access to those token balances. Beyond that, there are 3 exposed services. So these are services that you can connect to as though they were services on localhost. So that's the ingest service, runs on localhost port 8081. The search service runs on localhost port 8082. Unfortunately, there's a lot of tooling out there that assumes ingest and search are going to be on the same host, and in the development environment, they are currently not. If somebody wanted to put together, say, an HA proxy container that would make those things appear like they were coming out of the same host, that would be awesome. I would accept that pull request in a heartbeat, assuming it looked okay. And then the Ethereum RPC server is exposed at localhost port 18545. So if you have a dApp that you're trying to use in conjunction with OpenRelay, you would point the Ethereum server to port 18545. You would post orders into port 8081, and you would search for orders on port 8082. So to see what some of that looks like, here is a Massive pipeline. And if you're not familiar with Massive, I have not talked about it in a Screenside chat, but there is a blog post about it on blog.openrelay.xyz. Massive is a tool that we use for manipulation of 0x orders in bulk. So here we are going to start out with an order in a JSON file. We're going to set an expiration date that's 10 days in the future. I just happen to know off the top of my head that that number is 10 days worth of seconds. We're going to set the exchange to be the test RPC exchange. We are going to query localhost port 8081, that's the ingest service, to find out what fees we need to set on this order. The maker is going to take 50% of the fees, and the taker is going to take the other 50% of the fees. We're going to set a salt, which the default parameter for massive is to set a time, the salt equal to the current timestamp in seconds. Then we are going to sign the order with a private key that we have on our local system, replacing the maker with whatever address corresponds to that private key. At this point, the private key has to be on the local system. It can't rely on an RPC server. Massive does not know how to rely on an RPC server for signing. Again, that's something that I have on the roadmap and would love to get done. It's just a matter of priorities. Then we set allowances. So this is going to call out to localhost port 18545. So that's our Ethereum server. And it's going to set unlimited allowances for any of the tokens that correspond to the orders that are passing through this pipeline. And then finally, we are going to upload the order, which has now had expiration, exchange, fees, salt, and has been signed, and proper allowances have been set on the test blockchain. We're going to upload that to the ingest service on localhost port 8081. So that is going to get our order into the processing queue of OpenRelay. If you watched last week's Screenside Chat, you will remember that we have the delay relay in place. Now, it's not actually that hard to take the delay relay out of the development environment if you just want things to flow right through. But if you are maybe testing the delay relay or want to make sure you're testing the end-to-end system, you'll need to mine some blocks. So test RPC allows you to send a signal anytime you want to mine a block by posting a message that looks like this. And this is a curl command that you can just copy. And because it points to localhost port 18545, it will be the same on any system that's running the test RPC system that we just, or the Docker Compose stack that we just set up. So you run this curl command, it mines a block, it triggers the delay relay. You're going to have to run it twice because we have to wait for 2 blocks. And then everything gets moved through the system. So once you've uploaded an order and mined 2 blocks, you should find that the order is present in your order book. And to do that, you can do a simple curl search. So you can do curl-L. The -L with curl means that it is going to follow redirects. The orders API, under certain circumstances, may yield redirects which you will want to follow. So you follow those redirects and you get the order that you just posted in. It actually gives you a list of orders, but since we just set up this environment, it's only going to have 1 order for you. Does anybody have any questions about the development environment? Is anybody actually trying to follow along right now?
Yeah, ran through it just now. And what's the reason why it isn't trying to copy the CA certificates.cert from a Docker CFG directory into the etc/ssl certs directory inside the Scratch Docker containers?
So
if update build.
Did you run the 0xv2 branch?
No, this was from master.
Yeah, that's the change that I made to the 0xv2 branch, and is the reason I told you to run the 0xv2 branch instead of master.
Oh, missed that part. No issues then.
Yeah, so that I was aware of that issue, and I have already fixed it on the 0xv2 branch. I have not merged it into master because I haven't made any changes to master since I did that.
Okay.
Couple
Aside
questions.
Sorry?
A couple questions, Austin. One, is there any embiggen preloaded into the development environment?
No, there's not. That would not be a bad idea.
Oh, okay. I thought I'd ask that. And then for those who don't...
For what it's worth, all of the tokens that are present in the development environment are in an image that is provided by the 0x project team. We had to make a few minor modifications to the system for what we upload. The reason for that has to do with some pickiness around Ganache and the Go Ethereum client libraries. So basically, we had to make a couple of changes after the 0x project team's base image that they provide, but everything after that, we haven't added any contracts, we haven't changed any balances around. All of the contract deployments, the token balances, all of those are from the 0x project team's core image that they distribute.
Okay, cool. Second question, just for people who don't know, what's 0xv2?
All right. So this is probably a Screenside Chat in its own right. But so we talked in last week's Screenside Chat about what 0x is. 0xv2 is the next iteration of the 0x exchange contracts. So historically, 0x has only supported ERC20 tokens. In 0xv2, they will support ERC20 tokens and ERC721 tokens. There have been a handful of other neat features that have gone into 0xv2. In addition to that, they've kind of put in an abstraction layer where if somebody else comes up with a neat kind of token that 0x wants to support, 0xv2 could support new types of tokens without having to upgrade the core contracts. So they there's a, and I'm going to butcher the number. It's ERC 1115 or something like that is a new proposed token standard, and I have no idea what the current status of that is. But if that were to get adopted before they're ready to put out 0xv3, 0xv2 could be extended to support that contract or that token standard without having to deploy a whole new version of 0x. If you go to the 0x project's website, they have a lot of documentation about what has gone into 0xv2 and some of the differences between 0xv1 and 0xv2. But OpenRelay has been diligently building in support for 0xv2. As far as I'm concerned, we are ready to go live with 0xv2. The only problem is that it's running on Kovan, and Kovan is a proof of authority network, which has very similar problems to what we had with Ganache in terms of our Go Ethereum client not liking to communicate with the Kovan network. So we're working on those issues, and hopefully we'll be on Kovan with 0xv2 long before this video is publicly available. Other questions?
I don't have any more, but thanks for that reply.
Okay, so in production, what I've been talking about so far is our development environment. In production, we push our images to Docker Hub. They're publicly available on Docker Hub. We're an open source project. We have no reason to not make our Docker Hub images available. Anybody is welcome to go pull our Docker images, and you can even take our test RPC file and just run the Docker Compose pull instead of running Docker Compose build, and it will just pull them instead of building them locally. But if you want to make changes to the code and then build them, you need to use the Docker Compose build. So we deploy on production on AWS using the Elastic Container Service. So the Elastic Container Service is an Amazon service that basically lets you register virtual machines into Docker clusters. Then it takes the containers that you define, or the images that you define, and the services that you define, and it schedules those services to run on the virtual machines that you have joined to the clusters. And they handle all of that. If a virtual machine goes down, the EC2 auto-scaling will replace the virtual machine. But before the virtual machine is back up, the Elastic Container Service will have already redistributed those Docker containers to the other virtual machines that are part of the same cluster. So the Elastic Container Service has made managing Docker very painless. The only downside to the Elastic Container Service is that the configuration for it is specific to Amazon. So if you wanted to take your take your services that had been running on Elastic Container Service and move them to, say, the Google Cloud Platform or to Microsoft Azure, you're not going to have a great time with that because your configs are very specific to Amazon. We're actually working on a way to define our configs in a way that would be portable across hosts, but I'm not ready to talk about that in detail yet. I'd also note that before we ran Elastic Container Service, we ran Docker Swarm for a while. We found Elastic Container Service to be much more stable, and because we didn't have to run the whole service management platform in virtual machines of its own, it's also a lot cheaper to run on the Elastic Container Service than it was to run Docker Swarm. Docker Swarm is a good cross-platform option, but I was not really satisfied with its stability in my experience with it last fall. So next, CloudFormation is the tool that we use to manage our hosts and our containers. So CloudFormation lets you define all of the Amazon Web Services resources that you're going to need in a particular environment. So it goes everything from your network layer, your virtual machine layer, your firewall rules, your managed database service, your managed Redis cluster, your Elastic Container Service clusters, your Elastic Container Service services. All of that is defined in CloudFormation template. Originally, we had it in one just massive CloudFormation template. We have now broken that out, and the stuff that we are deploying for AWS or for OpenRelay's 0x v2 support is going into its own CloudFormation stack that still uses the infrastructure defined in the first CloudFormation stack. So we're kind of separating our infrastructure from our services in a slow, steady process. One of the neat things about Elastic Container Service is that all of the logging goes to CloudWatch. So that means you can go to the CloudWatch dashboard, or there are a number of other separate services that you can use to interact with CloudWatch. You can see all of your logs in one place. You don't have to log on to each of the Docker servers and go grepping through logs. They're all right there in one convenient dashboard. And you can set retention policies and send them off to S3 for to be kept permanently if that's what you're after. So the Elastic Container Service with integration with CloudWatch is very handy. One of the other neat things that we can do is at times that we have been at extra load, like when we were doing our embiggen exercise and trying to load 27 million orders into OpenRelay, we were able to add spot instances for extra capacity. So spot instances, if you're not familiar with the way Amazon Web Services does it, with a spot instance, you bid on computing resources, and there is a market price for those computing resources. So long as the market price is below your bid, you will get the computing resources. But if the market price goes above your bid, your virtual machines will just be terminated. And you get like 2 minutes warning before they're terminated, which is better than it used to be. It used to be no warning. So with the Elastic Container Service, we can add a spot instance into our ECS cluster, and we can use that extra computing power to process orders while we have it. And then if it goes away, then the services get rebalanced back onto our core set of virtual machines, and the processing will continue. It might be a little bit slower. We might see some backup in our queues, but that's why OpenRelay uses a queuing system, is to allow things to get backed up if we don't have the computing power to deal with it, because the alternative would be, as people are trying to push all of this in, we just have to reject their requests to give us orders. So letting things back up in queues is not ideal, but it's better than having to give people error messages. So that marks the end of this week's Screenside Chat. Next week, we have a few options for what I could cover. If you guys are interested, I could cover contract code. I could cover some examples of how to use Web3, or we could start digging into some of OpenRelay's microservice codes, start looking at the Go that comprises the actual services that we bundle into a Docker container and execute at runtime. I'll take feedback on what you guys would like to see next week after the presentation. But does anybody have any questions pertaining to the earlier parts of the presentation before we stop broadcasting? No questions? Okay.
None here.
All right, thanks.